Okay, in this video we're going to discuss section 3, elastic potential energy. Now that we have the general definition of potential energy, we can find other interaction terms inside of systems that can lead to potential energy. And one that we can easily find, and we have a expression to work with, is for elastic potential energy. So imagine a system like shown in the figure where I have a spring exerting a force on a block while it moves on a frictionless horizontal surface. We know if that block spring system is stretched out that the spring is going to exert a force both on the wall and on the mass attached to the end of the spring. So let's define the system to be the block, the spring, and the wall all together. So in this case, the spring is the interaction between the block and the wall, providing that interaction force. And because the interaction is inside the system, it leads to a potential energy. How would we calculate it? Well, we know the force acting on this guy, right? Hooke's law, that force is going to be minus K delta X. And if I integrate that over some distance, what I end up with is the functional form for the elastic potential energy. That the potential energy stored in the system is equal to half the spring constant times the change in the size of the spring compared to its equilibrium position. Right? Notice that this thing gets squared. So whether or not the spring is compressed by a delta S or stretched by that same amount, so say I compressed it by a centimeter or stretched it to a centimeter, in both cases, if the spring has the same spring constant, it gives me the same amount of stored potential energy in the system. So if I have a system now that has gravitational interactions, elastic interactions, and friction, but no external forces, I can write down my energy potential that says that if I look at the initial condition for my system, say I have a system that is being influenced by gravity and there's also a spring that could be stretched and it has some initial motion, I can calculate now all of these potential energy components and kinetic energy, and those have to be equal to the final mechanical energy pieces, kinetic energy plus gravitational potential energy plus this elastic potential energy, plus, right, the difference would have to come from any frictional forces that generate changes in thermal energy. So as we're adding in all of these different terms, this energy principle equation is starting to look more and more complex as we have more different types of energies to keep track of. But the message is simple and profound. A system that has no other interactions on it, the total energy of the system does not change but is conserved. It can be transformed in many ways, but that total is always a fixed value, and that's the key thing that we're pointing out here. So if we find that this is violated, then that tells us immediately that either we didn't keep track of some internal piece of the system energy, or there was some work done on it by the external environment. Okay, thank you. That ends our really brief discussion on energy conservation.